Hey Geometry, welcome to section 10.4, inscribed angles. This has got an example here. The entrance to a school prom has a semicircle arch like this. Streamers are attached with one endpoint at A and the other endpoint at B. The middle of each streamer can be attached to a different point P along the arch. And so what we see here is we have a whole bunch of, like, I don't know if you can see there, we got that there, and this example, this one here, and so on. And so what you can notice about these, which is kind of neat, is that, I don't know if you see them all, they all actually have like the same angle at where they attach. And in fact, this one in particular ends up being a 90-degree angle no matter what. So those inscribed angles are all the same, and in this case they all happen to be 90-degree angles when they're inscribed in this semicircle. So a neat property that can be used for a number of applications. So an inscribed angle has a vertex on a circle and sides that contain chords of the circle. So in circle C, for instance, arc or angle QRS is an inscribed angle, and it's comprised of two chords of the circle, so QR and RS, and so then that vertex is on the circle. So an intercepted arc has endpoints on the side of an inscribed angle and lies in the interior of the inscribed angle. So in circle C, the minor arc of QS is intercepted by that arc. So by that angle, that's inscribed angle. So this inscribed angle intercepts QS, that arc. So, three ways that an angle can be inscribed in a circle. So you can have the first way where the center P is on the side of an inscribed angle. So we have, there, in that case. We can have the center P be inside the inscribed angle, and we can have the center be on the outside of the inscribed angle. But those are all, three different ways that this can be done, and you can kind of work through and actually show kind of why this theorem works with this. So if an angle is inscribed in a circle, then the measure of the angle equals 1/2 the measure of the intercepted arc. So in this case, the measure of angle 1 is equal to 1/2 the measure of arc AB, which would mean that the measure of arc AB is equal to 2 times the measure of angle 1. So, if this was like, I don't know, what does that look like? Maybe like 65 degrees or something like that. Well, that means that this arc would be double that, so it would be 130. And if this was 130, that would be half that, so 65. And so you can use those properties to show this. All right, so let me go back here now and show you why it is exactly 1/2. And I'm not going to go full proof, but just kind of a quick explanation. If we take this, drawing up here, this first one, and so if we think about this arc measure is equal to that angle, whatever that is. And then this over here is an isosceles triangle. And so these two angles are the same. And we know from the exterior angle that these two have to add up to be that one. And so that means that this angle is going to end up being half that angle, which means that angle is going to be half of that arc. Pretty much the exact same thing goes on here, only you kind of do it twice. You'd basically show how, in this exact same way, that this angle is half of that. And then over here, we can do the same thing and show that these angles here are both half of this one. And so this full arc, and then this ends up being half that. And this one's a little bit weirder. You can do it, but it involves subtraction. So you can, subtract arcs away and get to there. So if you want to dive in and think about that, you can. But it still works out. It just instead of adding two angles together, we actually have to subtract angles. We can show angles and then that it works out. So using that property now, we can find a few angles. This wants us to find the measure of angle P. So angle P, this inscribed angle, is going to be half the intercepted arc. So this would be 35 degrees, since that's going to be 70 over 2. And then the measure of arc PO is going to be 2 times 56, which gives us 112 degrees. All right, so on the back, if two inscribed angles of a circle intercept the same arc or congruent arcs, then the angles are congruent. Let's write this symbol for that one. The angles are congruent. All right, so in this case, angle B and angle C both intercept arc AD. So we know that angle, the measure of those angles the angles are congruent. Angle B is congruent to angle C, and we know that the measures would be equal. So using that, here we have two inscribed angles intercepting the same arc. So we know that angle, STV is congruent to SUV. So we can say that angle STV is congruent to angle SUV. That's a U. And so we can set up and solve this, and they want us to find the measure of angle T, which I guess that is the only angle T that's drawn here. And so we can set these two equal to each other, do some algebra, and come back and figure out what angle T, whole angle T is once we figure out what X is. So set them equal, isolate the variable, so bring the X over here, get rid of this, get everything to the other side. And so we end up with just X on the left there, 20 on the right. So X is 20. We're not done yet, though. We're going to plug that in to figure out what the measure of angle T is. So the measure of angle T is 3 times 20 minus 5. So 60 minus 5 is 55 degrees. Would be the measure of that angle. All right, and then finishing off here with a proof. We're told that arc JM is congruent to arc KL. So JM, that arc there, is congruent to arc did I do that wrong? No, that's arc JM and arc KL. So that's what we are given in this case. They want us to prove that triangle JMN is congruent to triangle KLN. So we want to show that this little triangle over here is congruent to that one. So the first thing we know is, and they're kind of giving us some bits to fill in. So they gave us the given. So we know if these arcs are congruent, then their corresponding segments are congruent. So if minor arcs are congruent, then their corresponding chords are congruent. So we know then that this chord is congruent to that chord. And then we could go about this a couple different ways, but one way we could do this is we could say angle M and angle L intercept arc J, and they both intercept arc JK. Sorry, angle M and angle L intercept, I'm going to squeeze it in here, arc JK. So these two angles both intercept, and so that is the definition of intercepted arcs. And so this angle is going to be congruent to this one. Angle M is congruent to angle L. So we can say that angle M is congruent to angle L. And this is from the inscribed angles of the same arc are congruent. So inscribed angles of the same arc are congruent, so we know they're the same. And we could do something similar as well. We could have done K and J, those both intercept the same arc over here, JM, so we could do that. the quickest way to kind of finish this one off is actually, though, just vertical angles. So we got our old trusty vertical angles. So we could say angle KNL. KNL is congruent to angle JNM. Or MNJ, doesn't matter. And that is vertical angles. Vertical angles are congruent. And then from there we have angle, angle, side to show that those triangles are congruent. Though, like say, you could have done, if you want to do it, and you could have shown that these angles are congruent through that way.